Hi everyone, we're going to get started now and go into the webinar about how static analysis works, where we're going to go under the hood of how the overall field works and how a number of the products within this field are able to function by covering the core fundamentals. A bit of introduction for myself. My official title in Contrast Security is Principal Product Evangelist of helping communicate what we do to the overall market, but I have a significant technology background. So prior to being a member of the Contrast Security staff, I was a member of the Oracle Java team directly on the Java language and runtime itself in the role of Principal Product Manager, helping remedy a variety of the security issues that stemmed from the 2013 breaches. Prior to that, I was actually the product manager of a static analysis product, guiding the way for what that product did and how it would function. And some of the reasons that I'm particularly credible to speak about the role of static analysis in cybersecurity is that I handled the security issues in the JRE, that Java runtime, back when it was the height of its security issues. And I worked to bring in a number of features into that language, one of which is called JSR 308, to help incorporate it into the JDK for Java 8 that can facilitate the ability to do some static analysis. Beyond that, I was also the product manager of a very popular security static analyzer, so I have a bit of knowledge in that domain. So now, why is Contrast Security doing a webinar about the technical underpinnings of static analysis? And some of the reasons for this are that users frequently go through in their application security programs and they look to incorporate and do some comparisons between the context of RASP, or runtime self-protection, IAST, which is that integrated analysis, and then the SAST and DAST and a variety of other acronyms. And these discussions, when I listen to them and take part in them, they often focus on the role of output, of what are the number of false positives, what are the things that you deal with, and we don't go in and dive into the direct fundamentals of how the technology works in terms of supporting our ability to get that goal. And also, I want to go in and focus and provide a bit of a stable baseline so that if we do have a conversation about these underpinnings, that we can focus it on a few particular topics that are fundamental to the overall field. Now, if you're listening to this webinar, then you naturally have an inclination and just interest in the overall field of this fundamentals, but I want to keep in mind who I designed the content for and how I intended to communicate it. Primarily, the audience is towards developers and security professionals who are familiar with code. Maybe you write some, maybe you used to write some, maybe you have to evaluate it, but I don't want to go into the absolute total core fundamentals of requiring a computer science expertise. For example, speaking of myself, I don't have a technical computer science degree. My degree is actually in information systems from years ago. However, I was able to take that experience and knowledge and help lead a major language in terms of remedying their security issues. Now, the way that I want to walk through this topic is to go through and cover what's the base for static analysis, or what's sort of the root of the field. Then I want to talk about how code graphs work and why that model matters and how it incorporates the ability to generate results, followed by a data flow deep dive where we're going to go in and take a look at what happens along that code graph. Then we're going to piece everything together and use that to predict some results, or to predict those results' quality. So now we're going to go through and cover what is the base for static analysis, or what are some core fundamentals for the overall field. When I look at how static analysis is used in the security field, there's ultimately two books that are of relative significance, one of which is called Secure Programming with Static Analysis, that was written about a major security static analyzer and covers the fundamentals of how static analysis works to a point, as well as how it functions in the realm of security. Another major book that's the basis for a lot of the analysis field is a book called Compilers, Principles, Tools, and Techniques that's referred to as the Dragon Book, that deals with the role of data flow analysis and how code can be pieced together. So why do I choose that first book about secure programming with static analysis? The reason is this covers and talks about the goals of analysis, of what we want to accomplish, keeping in mind that the goal is to create those security results. And it covers those basic techniques of how data flow works, what data flow is looking for, what control flow is, what it's looking for, and it has a direct correlation to the field rather than theoretical in that it was written about an actual analyzer while that analyzer was being built. And the reason that I choose the Dragon book is that, in a sense, a static analyzer is really just a compiler whose goal is to produce security results instead of producing a program. So Compilers, Principles, Tools, and Techniques was actually the base of the other book upon which it was built, and it is a bit of a complicated book, but we're not going to be going through and building a static analyzer, so we don't need everything that's written in this book. It just covers the solid fundamentals of how things work. So I do want to say, if this looks like a complicated thing, or if you're thinking back to some computer science class, don't worry, we'll just ignore how complicated it looks. And what we'll do is we'll refer to a couple different chapters and sections within this book that cover the role of Introduction to Data Flow Analysis and SQL injection, which talk directly about the applicability of static analysis as a compiler to the field of security. So this book is very helpful if you're building an analyzer because it covers the core fundamental theories, but if you're just using an analyzer, it might be nice to know about this book, but it's not something that I'm necessarily expecting or anticipating that the majority of people will read. So with that, I want to get forward and talk a little bit about what is a code graph, how it works, and why it matters to the field of static analysis. So the reason that code graphs matter is because this is effectively what the analyzer does. The very first step that it has to do is to convert that code and possibly some of the binaries, if it's a binary analyzer or bytecode analyzer, into something called a graph. And that graph is not like a line graph or a line chart or your standard graph that you'd produce with Excel. There's an example picture of it over on the right here, in that it's something called a navigable graph, which is something that can be traversed and analyzed. And after it's converted that code into a graph, typically what the analyzer will do is it'll use a set of rules or definitions to go through and annotate that graph. So to tell the class or the function, what does a particular method do, what do things mean, or as we have something that comes in from a source or sink, which are terms that we'll cover later, what is it that we're actually looking for, and how do we know how to traverse this graph? Because as it goes to traverse it, that's where it looks through the data flow, the control flow, in order to figure out where possible risks can be within the application. Now, to create the graph, what it does is it uses something called a LEXER, which is a basic language understanding. So what are the semantics of how something actually works and what syntax actually means? So these languages are understood through something called a grammar, which identifies what specific terms mean. And a very popular parser generator for interpreting these grammars is something called ANTLER, which stands for Another Tool for Language Recognition. And this is used by language designers or people who want to interpret different scripting languages to figure out what something actually means. And so in the case over on the right, we have the canonical SQL injection example of select star from users where user ID equals test@example.com or 1 equals 1. And if we look at the parse tree that's been generated from ANTLER, we can see that there's a select statement, the select elements is star, and then there's a from clause which incorporates the where clause. So the from, the table is just users, which if we traverse down that tree we'll see. And then over on the right, we're able to break down those two different expressions there, where there is an expression, but it's made of two different expressions plus a logical operator of OR. So by having broken this statement down, I'm able to actually look at what each particular piece of this language means and make a determination in terms of what the actual query is. Now, ANTLER also offers a number of different language parsers and grammars that are already publicly available that give a basic language understanding. So they cover things like, what is a variable, what does assignment mean, how do I understand what is a function call, and where do different words go. Now this is just a basic language understanding, so the next step that someone would need to do is typically to go through and make sense of what this does. So what is an example hierarchy of this? When we go to call a function, how do we know what that function actually is? And this is where that context of building a graph and interpreting those frameworks comes into play. So now let's look at what we use this sample code and this analysis and an understanding of a language in order to analyze. And let's look at some basic code that represents how a SQL injection functions. In this case, what we have is request.getParameter, which we identify as a basic request, and then as we go through to build the structure, we annotate that getParameter, its return value, is of a remote user input type. So we propagate that taint over to that username through the equal sign. Then that username gets concatenated into a string over here on the right side, where username is used in a basic select query. And ultimately, because the string is concatenated through our understanding of the language and what that plus sign means, that propagates over to the SQL over in the left through the same assignment or equal statement that we understand as a result of having the grammar for this particular language. Then finally, we have that SQL, which is being used in a function call there for statement.executeQuery, where we've provided some definition to the analyzer of what execute query means, in that it should not accept a realm of user input that came from SQL, which came from username, which came from request.getParameter. So this is an example of how data flow functions and what you want to look for across code as you have an understanding of its language. If we want to look at this in a basic graph traversal form of how this looks, you can see over on the left there's the request.getParameter that flows into username. That username flows to create a string based on that username, and that gets assigned to a SQL statement, and then ultimately that SQL statement is what's used in the actual SQL query. So each of these is a representation along that graph, and in graph analysis terminology, each of these is referred to as a node, those circles, and then the lines between them are directional edges. So this indicates the flow across that application. Now, what does a code graph actually look like if we look under the hood at what some sample code means? It's covered in that Dragon book, that Compiler's Principles, Tools, and Techniques, in terms of the definitions of statements and blocks. And what we can see is that an individual piece of code that someone would write over there in the leftmost diagram that says source code is transferred into a set of blocks of how this code will execute and call along itself. And so in this case, we have a set of variable assignments followed by an if, and if that statement is true, it goes to the block right below it, and if that statement is not true, then it goes down to the one a little bit lower. So this is how the control flow looks across a graph in order for data flow to work across that control flow as the application executes between those different if statements and all the various conditional branches that an application has. So in order to do a code graph, you have to have some level of control flow analysis in terms of what is going to execute and when. And now we're going to go through and do a bit more further analysis into data flow and how this actually functions. So first, I want to go into the realm of what is it that we're actually looking for. Because as we did that basic semantic analysis of understanding a language, that lexing that we did using the parser generator of Antler is really just an understanding of the basic words. It doesn't provide any actual context as to what those words mean in terms of how the program will execute. It only tells us how those words can relate to each other. And when we go to do an analysis for static analysis, when a function is called, we want to know what that function actually is. So this is a technique that's done that's called type resolution. And there's two types of languages in which you would do this level of type resolution. The first are statically typed languages, which are things like Java and .NET. And then the second is what's called a more dynamic language of things like Python, JavaScript, Ruby, where all items are objects, and you don't necessarily know what those objects are in advance because the methods are a little bit more dynamic. Contrast this to Java and .NET, where everything is fully defined and classes have individual methods and properties. So if we look at how this type resolution works in terms of static languages, it ultimately works in the same way. We look up a class, we look up like my class extends another one, which might be its parent, and it implements a variety of interfaces. So the way that Java applications are coded, for example, you can extend one class, but you can implement many other. So what we would do here is to look up the hierarchy of what my class is and what's everything above it. And the way that we would have an analyzer that goes through and figures out what the functions are is if a class extends another class or implements it and has and overrides something that's in that superclass, we have an understanding of what happens in my class because we understand the parent within this hierarchy. So the benefit of this in terms of static languages is that all of these methods are clearly understood because there's that type contract in the interface and class definitions. An example of this in terms of type resolution for things like database drivers, which we know have SQL injection capabilities, we have the definition of a JDBC driver. So any class which implements that driver, whether it's MySQL driver, PostgreSQL driver, the Oracle driver, it ultimately has those values or those functions from its parent, such as execute statement. This is the function that you don't want those terms to get to of user input because that's the definition of a SQL injection. So what we would do is we would look and we would say, well, my driver is a JDBC driver, and my driver implements the method called execute statement. Therefore, this execute statement is going to talk to a SQL system because I know that's what its parent class is doing. So the nice part about this is that the system's able to understand that method above of knowing what the JDBC is, and then apply that knowledge to the actual mydriver.execute statement in order to know that method's intent. Now, some of the terminology that we go for to look for within an application are things like source, taint, pass-through, validation, and sink. And the most important ones here are the definitions of sources and sinks. And source is where data comes from. So something like a return value when you have request.getParameter for a legacy Java EE application, or in the case of a more modern one that uses like JAX-RS or JSON endpoints, you might have a basic getter on a property. And those ultimately come from a source of something like a user. And a sink is a location of where that data is actually used. So things like statement.execute query, runtime.exec, the file constructor, and these are the locations that you don't want the source to be. But that source has to flow through an application in terms of just making it from source to sink. So what we do when each source comes in, we apply some level of taint flag to it that indicates what type of source it is. A thing like a remote input, is it parameters, is it command line input, or just what type of source is it, because we want to make sure that we don't treat each one with the exact same threat context. Then that data flows through the application using a series of pass-throughs or transfers or traversals in terms of how that taint can move from one object to another. For example, over on the right, we could have string s equals word plus taint, at which point the value of s comes in from the value of whatever the taint flag is, and it just gets propagated and passed through to that other object. At the same point, you could have myObject.setName where you add it to a property, or things like stringbuilder.append, or string plus other string. Then there's ways of validating these before they come to a sink, or we want to be able to detect what is safe. So in this case, something might go through a method called encoder.encodeHTML, which marks something as safe, but it's not just safe or unsafe, it's safe for what particular context. So for example, if I make something safe for a cross-site scripting context through encoder.encodeHTML, I can't necessarily go and pass that same value into execute query because I need a different level of validation. So like sources have taint types, validation have validation types. To look at this in a visual flow across a call graph, ultimately what we have is source, that edge of where, or that node of where something comes from, going down to a pass-through, in this case an assignment, and you can have multiple pass-throughs here. So we have SQL equals select plus param, so that data passes through, and then ultimately it goes into that sink of executing the SQL statement, which we know came from the value. In the same way, that would go with validation, where we have a prepared statement there, which is how you validate against a SQL statement, and ultimately it would make it down to this prepared statement.execute. However, this would be safe because it would break the navigable flow between source and sink. Now, one of the issues with this is the context of wide propagation of when we go to do this taint propagation or pass-through, how do we know where to actually apply that? So in this case, we have some basic code there that just says string username request.getParameter of the username, and then we put that into a map. A map is a very common key data or key value data structure that's used by a number of applications to just track a large variety of points of data. For example, request parameters are maps. Maps are used all throughout. There's a lot of things that implement hash map class. It's very common. So in this case, a lot of static analyzers will go through and they'll do sort of a cheating attempt. And what they'll do is when they see something that's tainted go into the map, they'll mark anything that comes out of that map as tainted. So 2 lines down below where we say string select equals select plus map.get of a constant, what will happen is that will frequently get flagged because that element there, that constant, comes out of the same map that username went into. And one of the reasons that this is done is for efficiency, or because those keys there placed into map.get are not constant or not known, so the analyzers will attempt to make up for this by assuming that we don't necessarily know what's coming out, but I saw something bad go in. Now the problem with doing this in terms of things like maps is that there are a lot of points of data that go into maps. They're a bulk data structure, so just automatically tainting anything that comes out of it is going to generate a lot of inaccuracies. Now this level of wide propagation in terms of static analysis is not necessarily solvable. And it also affects things like arrays and lists, those map key value pairs, and it may in some cases be possible to solve this, but at a general scale, it's not. And one of the reasons for this is that those analyzers will do something called static single assignment as a general optimization in terms of how they find data to track. And what static single assignment does is it makes sure that each variable is used and assigned once and only once. So through that, if something is only assigned once, then you can always identify what it is. So this is a thing that's done under the hood within the compilers and within the analyzers in order to help them track. But the problem is that when something goes into a map and something else comes out of a map, and a map is a bulk data structure, you can't do static single assignment because there's no definition of what is static. The map is static, but the things that go in and come out are not. So you're not able to do this level of optimization here in order to help you track. And the ultimate reason that this wide propagation is bad or is harmful in terms of the static analysis field is this is actually the source of a number of the false positives that people might see within their application. So you tend to get a little lossy results when you deal with things that are the more dynamic data structures. And unfortunately, these are also some data structures that are covered in Computer Science 101 just after people are able to compile their applications and run them. For example, there are things like lists or arrays or sets or maps or any sort of data structure that deals with multiple items and doesn't have a guaranteed set of order of what comes out. So it's very easy when code is written in terms of string SQL equals this, and you have one thing to track. It gets a little harder when you have to propagate across these data structures. And the problem is many applications will do this, will use these data structures all throughout, and therefore they end up tricking those analyzers in terms of doing the wrong things. Now it also becomes a little more difficult with the context of dynamic languages in terms of something that they do that's called duck typing. So in statically typed languages, you generally look up a class, you look up a hierarchy, but the problem is in duck typing languages like Python or Ruby or JavaScript, there isn't necessarily a clear hierarchy there, so you have to look at the convention of how things are used. The term duck typing came from the realm of if it looks like a duck and it quacks like a duck, then you should let it act as a duck. And when you do duck typing, you need to have a lot of rules for those frameworks, assuming that you were able to pick up on the convention. And the problem is that these rules are frequently a realm of guesses. So are we able to go in and figure out if the source and sink is actually there, because the code might not actually be there? Now the example of how this is done within the Java syntax is this basic statement here of results rs equals statement.execute query, and we just pass that basic SQL query in there. So now we know that statement.execute query executes a SQL query because of what that function actually is. The term designed by contract applies, and execute query doesn't really change. Its goal is to execute a query. Now, the difficulty with type resolution in these dynamic languages of figuring out what the equivalent of like execute query means is that those methods can actually be added dynamically. So a lot of the frameworks in things like Python, the functions are not actually even there on the original object. They're applied in by the framework as something runs. So in order to determine what something is, in order to figure out what the function that's being called will actually go to without running the application, essentially requires a level of data flow analysis to figure out how an object is used and where it's used and what properties it has so that we can figure out statically without running it what that application actually means in terms of where a function would go or if it's there at all. Now, an example of this in terms of method overriding for Python is we can actually import a class from another package and define new behaviors on it. So in this case, with someClass.update equals update, what we're doing here is to either add or override the function of what update does. So the difficulty here from a static context, which is a non-running application, is that the value of that sum class, the function, is actually changed at execution. So if static analysis occurs before execution, then that method cannot actually be on the call graph because it's not actually there. Now, another difficulty with this is in the vein of Java 9, where there's a feature added through something called JEP 238, which has the definition of multi-release jar files. And I've drawn an arrow here in terms of indicating that this feature is closed and delivered. And it is available in all instances of Java since Java 9. The reason that this was added was to give people the ability to utilize the newer language APIs and the newer syntax without breaking compatibility. So for example, you can have an application that's compatible with both Java 8 and Java 9 and Java 10 and 11 and so on, without breaking that compatibility, but also using the newer APIs, which are not present in the older one. So yes, older versions of Java 8 and below could compile for lower versions, but the problem is once you started using syntax and functions that were not available in the old versions, you would break compatibility. So this was added to help library authors update. Now, the reason that this poses a difficulty for static analysis is that you can actually have a different class that goes by exactly the same name. So in this example, I have something called com.example.multirelease, and I have two classes in here that are called doSomething. They're the exact same package, they're the exact same class name, but they have different behavior. And this JVM, in this case, will decide which of them that it wants to load. So we'll notice that up above in the source packages, I just have the basic one called doSomething, and the one down below is also called doSomething, but it's in a special directory called Java 11. So the difference is that only Java 11 and above will load the lower class. However, Java 10 and below will load the higher class, that doSomething that's up above in the normal source tree. So if I'm doing a static analysis before the application actually loads, it's possible that the static analyzer will open the wrong class either above, or it will have to generate multiple execution paths in terms of flowing through each of those methods. Now, the difficulty there would be the deluge of other issues that creates in terms of the sheer number of paths that it needs to make, assuming more than one class appears. And some other terms that we can use in terms of static analysis are things like global and local. Now, the official science terms for this are intraprocedural and interprocedural, but global and local are much easier to say. So intraprocedural is typically where something is done within a function or within a small scope. This is a small area to look at, and interprocedural is something that's effectively across many functions or throughout an application. So for that wide propagation that we were talking about before of working through lists, sets, and maps and being able to taint things or know that a key is constant, that may be solvable in certain cases for this small local analysis where it's used in a very small subset. However, that would be difficult. But the sheer difficulty of solving that at scale, for example, where a data structure is used in an object property, where it frequently is in frameworks like Hibernate and other locations, it's going to be very difficult to figure out, are those keys actually constant? And we're only able to make a determination from a static perspective if we're able to do optimizations such as static single assignment. So it may be possible to deal with that wide propagation problem, however, not in the majority of contexts in which they're used. Now, another location that might damage the ability to construct a call flow graph is frameworks such as inversion of control, dependency injection, or any location by which the definition of code and the calling of that code is not clear. So in the case of inversion of control, that code path is created by the framework, and it's not actually a direct call from one point to another, and it's in fact a separate rule analyzer that has to go through and figure out what is the intent when control is inverted in terms of how the application gets called. Now we're going to go in the context of using the information that we've learned about constructing a code graph and talk about predicting results. And this is important as you go to scale any technology across your organization, because it's going to help you understand what you'll get as you encounter each application team or deal with different languages or just teams that do things differently based on the needs of their individual applications. The main thing to remember is that analyzers themselves are largely just a set of graph traversals. And effectively, anything that impairs the creation of that graph is going to impair the results as well. And this incorporates basic utilities such as lists, sets, maps, or anything that goes into these bulk data structures, and that includes things such as JSON endpoints, which are the end of those basic REST calls, or if you're using a framework like gRPC, it will include that as well. And then lastly, that static analysis works better on static languages or locations where code has a very strict definition. Now, regarding the ability to perform those graphs on different code bases, with your static type languages, we have a little more success in the field than we do with dynamic languages. But static analysis is not without its challenges in those static languages, in that it has difficulty with something called a non-imperative style of coding, such as inversion of control, or places where there is not a direct code correlation and that code is constructed at runtime itself. Now, one of the difficulties with this is that the Java language itself is becoming more dynamic under the hood, both in terms of the ways that developers can write it and the way that the system will execute it. For example, in Java 9, there was that implementation of multi-release jar files where you can have a different class by the same name, which will provide difficulty to the ability to graph that and figure out which one is right. And similarly, in Java 10, there's something called a var syntax, where you don't have to define what a variable is, and actually the compiler itself will produce that, use that determination on its own. You can just say var s equals and then a string, and the JDK will interpret that that is a string. So yes, the compiler can do that in many cases on its own. However, the definition of var requires an analysis to figure out what that type is, and any analyzer would need to support that more dynamic language capability. Now contrast this with dynamic languages where you have a low to no success in terms of being able to generate results, and one of the reasons that you'll have that low to no success is a difficulty in resolving what those functions actually are, since they aren't necessarily existing in the code base because those functions are added at runtime. And even if we're able to resolve what those functions are, there are a lot of difficulties in connecting that graph. So with this, there's a lot of commentary that can be said about different types of analysis, such as web applications might get false positives. Well, my applications will get good results. Or someone will say, well, you really just need to tune the rules in terms of what you see, and you can filter it later. But the better question when I go to analyze applications or to work in the overall field is a question of, can this actually be converted into a graph that's in a very helpful form? And if it's not something that can be graphed, how would I know the difference between something where there's no result and something where I just had a major difficulty with the graph? Because that's a very hard thing to tell unless you actually know how and where to look. And the problem is you either won't get any results or you'll get a deluge of false positives because there's a connection that should only be traversed in certain cases. And in terms of filtering results, it's better to just not generate those paths rather than to produce a whole bunch of paths, generate a bunch of false positives, and say, well, you just need a better visibility in terms of filtering those out. A better case is to simply not produce those false positives at all. And with that, I want to go through and do a bit of a recap of the information that we've covered, where we started out talking about the basis for the static analysis field in terms of the fact that a security static analyzer is in essence just a compiler that produces security results instead of the compiled application itself. The overall structure that these applications use in order to do their static analysis is what's called a code graph. Both a control flow graph that it provides a definition of what code executes and when based on if statements and conditionals, and we talked about why that model mattered. Then we went into the data flow, which is how we can trace an actual threat through an application from source to sink, talking about what it meant to be a source, a sink, a pass-through, a taint, a validation, and how each of those terms interplayed in terms of what it is that we want to look for. Then finally we spent a little bit of time putting that together and talking about the ability to predict results and to look at a couple different application development strategies such as inversion of control and the use of dynamic languages in terms of being able to understand if we use these, what will be the impact on our security results. And with that, I just want to take an opportunity to address a couple of the questions that we've received in the comments so far. All right, so I want to go and take an opportunity to answer some of the questions that have come in just as we've been walking through this webinar. And it looks like the first question that we have is, what is the difference between static analysis, which we just covered, and integrated and runtime protection in terms of how they work? So the major difference between these two is the visibility of the graphs. So whereas static analysis focuses on a simulated graph of control flow and data flow, a runtime analyzer, be it IAST or RASP, is really just sitting on watching the execution as things flow across the execution graph, which is like a combined version of the control flow and data flow that's put together by the actual runtime. So one of the reasons that the IAST and runtime capabilities are able to have a higher level of accuracy is that they use the actual graph that occurred rather than sort of figuring out how frameworks are pieced together. Right. And another of the questions is, I use a particular product. I'm not going to say which one because I don't want this to discuss various products in particular. How does this relate to the static analyzer that is in use? What I wanted to do today was just to talk about how the overall field works, because we might have a lot of commonalities or ways that analyzers, static analyzers, are able to differentiate themselves, but ultimately there's a lot of common ground in terms of what the field would do. So what I wanted to cover was the level of like what we would learn inside of a university course or something if we studied how to build static analyzers or how they function under the hood. And what we'll find as we look at an individual product, whichever anyone happens to be using, is that pretty much all the commercial and open source analyzers, they go through to do their own special thing in terms of how they differentiate, but there's a lot of common ground under the hood. So for example, one of the items that we talked about was the context of lexing, which is how you get the language analysis of understanding what the language syntax itself looks like. That's common to every single analyzer out there, so I figured by covering that we have a lot of commonalities to understand how these things make their determination and start picking out their results. Similarly speaking, that wide propagation problem, it needs to be solved in the field before it can be solved in a particular product. That would be the field of static analysis. All right, and with that, I just wanted to take an opportunity to thank everyone for coming and listening to the webinar, and please feel free to reach out using any contact form if you would like to have any further questions. Thank you very much.